Okay, so we'll see if anyone else trickles in, but we'll just go for it here because we got a lot of fun stuff. It's just basically a bunch of pictures of cool planes, so hopefully we're all cool with that. And we'll be talking about a lot of different concepts. So quickly, we'll go over some like high-speed flow stuff, some people just to make sure we're all on the same footing. Then we're going to talk about the different speed regimes, and as we kind of go, we're going to talk a little bit about the different design considerations for each type of airplane that has to operate in that. And and we'll look at pictures of cool planes. It's good stuff. So just to start off, review of fluid dynamics. We love fluid dynamics, kind of. High-speed fluid dynamics is cool. Pressure waves, right? Whenever we push something or we have in contact with a fluid, like any sort of material, the energy and like force gets transmitted as a wave of pressure. And you can kind of see like the gas, it's going to take a minute. In 3D space, we often look at these as circles, but they're actually like big spheres that are going out in actual space. It's going to be depending on material density and temperature, and will depend on, when we call those speed of sound. I think we got that. And we always love our pictures of like a little plane. As we move, we get a lag. The main thing to note is that the pressure wave moves only relative to the surrounding fluid and not the aircraft. So if I take, the best method, it kind of feels weird, but if I like fire a gun in front of an aircraft at Mach 1, then the bullet is going to travel at whatever the speed the aircraft is plus Mach 1. But if I try and send a pressure wave forward from an aircraft traveling at Mach 0.5, it can only travel forward at Mach 1 relative to the air, so that means it only travels at Mach 0.5 relative to the aircraft. That makes sense. The speed limit is relative to the fluid and is not measured relative to the actual body moving through it, which makes you a unique phenomenon where they like seem to stack up slowly. So as you go forward, the pressure waves can't go much faster than the aircraft, and but they can move directly backwards. So when you're going like Mach 1, your pressure wave can be traveling backwards at Mach 2 relative to you. So things are changing. You can see that like on here where the circles are a lot wider in the back. Right at Mach 1, they stack up perfectly, and as you go back Mach 1, it makes like very little conceptual sense when you look at it, but it like makes nice geometrical sense when you look at those circles and they form like a nice triangle going backwards, which tries to give you an understanding of what's happening when you have a shock wave. But the main thing, pressure waves stack up, make shock waves. And then the big thing is when we get to this like high-speed flow, it's interesting because when you're at kind of low speeds, you're always dominated by like Reynolds number is like your main factor. Exactly, the velocity is changing relative to the viscosity of your fluid, and like that's your big condition for like what does my flow look like. Once you like go really fast, especially when you get like hypersonic, like past like Mach 10, like the relative Reynolds number of the fluid just does not matter. Like the only thing is Mach number, and that's it, because it defines the angles of all the shock waves and how pressures and temperatures are increasing, which we'll talk about. All right, and again, before I get too ahead of myself, all on the same footing, incompressible flow, right? Hamburger. The main thing is, like when I look at this, if I look at the streamlines on the hamburger, like they're nice and smooth. Like I can draw a nice smooth line through all of these points. There's like no discontinuities where they change sharply in any angles. Everything is nice and smooth. And then the other big thing is, kind of ducts, which we've all worked with this stuff like in fluids class, right? If I decrease the area, it speeds up, right? JD knows this isn't true anymore though when we get to compressible flow. And that like makes sense. Faster, lower pressure, density stays the same. Makes a tons of sense. And then we get to compressible flow. When we start to go past 0.7, although the delimitation there depends on who you're talking to, and density is not constant anymore. And then things just don't make sense anymore. They just go contrary to everything that we normally think about.
Isn't that supposed to be 0.3?
It's 0.3, 0.7. I like 0.7 more just when I think about it, but yeah. Well, it's like the lines, like how different are they? When you're at 0.7, like nothing is the same.
Mach 0.3 is for at least over an airfoil that exceeds 1%.
Yeah.
Right.
I think that's just what number I remembered from, but yeah, they diverge.
I thought it was because transonics at 0.7.
Yeah.
Shock.
No, that's a good. I think maybe I was writing down the transonic number then. Anyways, so Also love the cow image. But now the big difference that you have to think about is the converging duct. When it gets smaller, your flow slows down and your pressure increases, and so does temperature and density. So I thought I was going to grab this. So your big thing is when you have a nozzle, which is the common example, that you have Mach less than 1, converging duct, smaller area, faster speed, lower pressure, normal shock, and then greater than Mach 1. As you go this direction, your area is increasing, but your velocity continues to increase. Density continues to fall, pressure continues to fall, temperature continues to fall, which is why we love these types of nozzles. What I want to note, because I'm trying to give people like a conceptual understanding, because like the actual math of like hypersonic fluid dynamics is just like bad. I like to imagine incompressible flow is like you're like in like a race with a bunch of runners, and you can see what's happening. And a bunch of people are like going in a direction ahead of you. You can see that, and you kind of like match. Like everyone's kind of like one like hive mind as you're running as like this big giant group. Doesn't really happen in a converging duct that they might all speed up, although it happens a little bit. And then I like to imagine when you go to compressible flow, especially once you go past Mach 1, that instead of a bunch of runners, you're like a bunch of people on a highway with blindfolds trying to go as fast as they can. And if someone stops ahead of you, you're not going to stop until you slam into the back of them, and that's the only way that you're going to find out about it. And then if you are trying to say, well, how fast am I willing to go on a highway when I'm blindfolded? If I go down to 2 lanes with a bunch of people on it, you're going to go really slowly because you don't want to crash into anybody. But if I open it up to 20 lanes, then you feel more free to just go as fast as you want, because the chance that you're going to hit somebody goes down. So that's kind of like a conceptual way of trying to rationalize why this is happening. But now you switch that. This goes out as your density is increasing. Your cars are getting farther apart, but they can go faster. All right. And we talked about flow, now have shocks, which we're going to talk about. Cool. I'm doing on time already. Alrighty, so shocks. Whenever we're looking at your high-speed flows, these are what you're kind of looking for, because they start to define how things behave. Anytime flow changes direction, you get a shock, just like any time at all, once you pass Mach 1. So the most traditional case is that you have air going faster than Mach 1 over a flat plate, and then the flat plate changes direction at some beta, and right here, you're going to get a shock wave as it changes direction. And the exact angle of this is a lot of it's actually not that bad of math. It just depends on Mach number and theta, although it's not an easily solvable. You have to do it with a computer. And as this guy goes, here it makes sense. You hit this plate, you have to turn, you make a shock wave. But now when air goes into the shock wave, it also turns up here. So remember when we were talking about incompressible flow, you have these streamlines where I can trace it out nice and neatly, no discontinuities. But when you get to this, there actually is. You go straight, and then because these are like 1/10 of a millimeter thick, it just looks like a straight discontinuity of change of angle. And if you really want to know, because usually it's taking out, this has like a velocity vector here, and it's taking out this velocity vector, goes away, and then it switches to here. I'm going to work through all that math right now, but discontinuous. There also are expansion shocks. They make less sense, but when flow goes over this, it's a continuous change in angle, and instead of a flat kind of shock, you get like a region of expansion, but it's a little bit harder to visualize. I believe like these guys here, as the body tapers backwards, you can see how they're kind of a lot wider. Those are your expansions. As you go through them, especially these guys, you're increasing your density, pressure, and temperature all at the same time. All right. Cool. Now this is X59, the research one who's trying to reduce the noise. So you can notice here, all of these, they seem much harsher than the ones in the bottom. So they're trying to make the shock waves going downwards towards the ground much weaker, and all the rest of the strong shocks just go straight up. And the right one was a stalled. So if you can watch this, what I want you to look for is shocks that are straight up and down. They're vertical lines. And what they are is they're delimitations between when flow is going faster than the speed of sound and less than the speed of sound. And they really love to mess with you. So when you're designing engines, especially like if you have your afterburner, what happens is if you design it wrong, your normal shock can kind of travel up and down a tube. I still have not found a conceptual way to do this, besides you can kind of think of the pressure on one side and the pressure on the other. If the pressure behind the normal shock is getting too large, like say there's a new block in front of it, then the normal shock is going to travel backwards. Because imagine on this engine here, this is flow coming in at the speed of sound. If I blocked this off and flow could not go any further right here, what would happen is I would get an enormous bow shock on the front of it, or a really powerful shock wave. And it's super powerful because it's going to take the flow that's already well past the speed of sound and decelerate it all the way down to subsonic, because it has to, because these like regions they have to have no flow in them because it would be blocked. Once you open it and flow can actually continue to move, then you can make it so there is no normal shock. And this is a special case. This is called buzz, which is a pretty a topic under research. When this stuff happens, this is actually playing through time, and the normal shocks are going back and forth, and the shock waves are changing, causing it to buzz.
The simulation that we just watched, what's it a simulation of?
So we're going to talk about this engine in a minute. So this is a ramjet. So it has to get the flow less than the speed of sound. And we'll go over why that is and how that's supposed to be working. It's a little bit hard to explain right now. But it's a type of engine. And this is specifically the intake for that engine.
What's one of the ramjets spike in the middle there?
This would be like a 2D sim, so you could actually have like struts and stuff. They just aren't simulating it. Okay, so then we get to our flight regimes. So the only actual like main delimiter here is like Mach 1, which we already kind of erased. Because subsonic, no supersonic air anywhere. Transonic, we're getting some supersonic air. Supersonic, everything is above Mach 1. And Mach 1 isn't even like in here because, as we'll talk about in a second, you can get supersonic air when your free stream velocity is less than Mach 1. And then everything else down here, 5 and 10, are they're random in the sense that there really is no difference in flow between Mach 4.99999 and Mach 5.0001. There's just, you can't tell a difference between the two. But there are technological differences in why we might split these up into regimes that we're going to talk about. And the vehicles are also, you can definitely have things that are exceptions to what I just wrote. All right. And real quick, to kind of summarize in some of the different things that are going on, I'll play that in animation a couple times. So as I said once, this is a bow shock. So it's just a really powerful shock that's forming on the front end of a body. We blew through it right here, but we're going to form some normal shocks over this airfoil as it starts to go supersonic right there. Down here we have pressure. So you can, I don't have a good, I wish I had more time to do this in more detail. We can see it's really red right here. It's because as our air comes in and decelerates, it's hitting a body, and it needs to slow all the way down, so there's like a stagnation point right there. And when I take super fast air and I slow it down, I get a ton of pressure, which just translates to pressure drag right on the front of your airfoil. And then you can kind of see how temperature on the bottom there is spiking. The maximum red is, I think I set it to 2,000 Kelvin. So as it actually starts to get yellow, that's really hot for it to show up. All right. First design thing. We got through the fluids. Yay, we made it. Time to think about planes. All right, flow separation. So when people were trying to figure out how to actually go past and approach the speed of sound, one of the main things is that their control surfaces decided to just stop working for some reason, which is kind of annoying. The reason is because as you form these normal shocks over an airfoil, So airfoils speed up flow over the top, decreases pressure, creates lift, right? That's what the shape is for. So on this one, as I'm accelerating, I eventually exceed Mach 1, and I form a normal shock. And one of our big problems with normal shocks that really cause us problems is that they often cause flow separation. And flow separation creates a really turbulent boundary layer. And if I have a large section of separated flow from that, and my control surface is right here, my control surface can't do anything. It doesn't matter if I'm deflected down or up, I won't get any change. So to combat that, you can't have just a single little surface on the back. You have to have what we call a full flying elevator, like this video was playing of the F-16. Please play the video. So these are full. So anytime it's moving, it can actually use, like once it gets up to like Mach 2, it can use the actual shock waves if it really wants to move itself back and forth. But you don't have that problem with separated flow because your entire thing is a control surface at this point. And I couldn't find any actual good images of this, but this too is also on a rod, and it fully deflects back and forth. Any thoughts or questions about that one? No. All right. And we get to mix this with another thing that makes things even worse. So, if you look on the top right up there, it's a graph of pressure over an airfoil as we go faster. So it's playing that same thing, but you have pressure coefficient. And the main thing is in your kind of subsonic incompressible ranges, the moment around your airfoil can change a little bit, but it's going to stay like kind of the same, at least relative to velocity and not angle of attack. Angle of attack, it'll change. But once you start going to Mach 1, the flow around the airfoil changes, and the actual like moments and forces that your airfoil is causing begin to change and shift. So the actual thing that happens is that your center of lift changes. So to erase this again. Myself a piece of chalk. Now I get to learn how to draw planes. So normally we want our center left to just be here, and our CG is, well, you have us summed with these guys too, and we have our CG, and everything is fine. But as we start to go faster, our pressure is going to start moving backwards. So instead of this being here, it's here, and instead of it being here, it's here. And instead of us being stable anymore, we now have a pitching moment trying to put us into a nosedive. And when you combine that with the previous problem, where as you go faster, I lose control authority, you now have a problem. So the really fun fact is like the P-51 and other like World War II fighters, extremely overpowered. But if they wanted to, they can go climb to like 40,000 feet and then put themselves into a dive. And I think the listed top speed was like 0.7. So like a little bit under, or was it 0.5? I was reading this last night. Like they were starting to approach the transonic region. And if they put themselves into a dive, they could start approaching Mach 1, definitely getting into transonic. But they put themselves into a death dive because they can't get back out of it, especially if they go too fast. Once they are well within transonic, normal shock forms on the elevator in the back. They no longer have control authority. And this Mach tug phenomenon, which continues to push them deeper and deeper into a dive, just makes the problems worse. So a lot of aircraft just straight up crash that way. I also found that there's this Swallow aircraft that apparently the British made that was trying to do what the X-1 does that we're talking about in a second to kind of explore high-speed stuff. I don't know that much. I just know what I've read and have experienced, but that does not look like something that would do well against either of the problems that we just talked about. So I think the two that they made both crashed, unsurprisingly. So when we come to actually designing things, you have to be super careful, and this is like kind of our initial control problems. And then unsurprisingly, drag is a problem. I know that really surprises a lot of us. However, there's a unique issue now when we get to transonic and supersonic, which is called wave drag, which is just characterizing the additional drag happening from kind of approaching the speed of sound and creating shock waves. So when we were looking at the case 42, case 49, a second ago, all the shock waves from the CFD, those are making drag. Those big pressure spikes slowing down the aircraft. And there is a special type of body called the Sears hack body, which is mathematically supposed to minimize the drag created from shocks. So the design principle, and the reason it is that is because there's this area rule that you want to follow, and it's the best at following that area rule. And I don't know why, I just accept it as fact right now. So if you want to evaluate your aircraft and see, well, am I doing the best possible job to minimize wave drag specifically? Because as you go faster, that becomes to actually dominate your other factors of drag. So you have to design for that if I want to go faster or approach the speed of sound. And so what you do is you take your aircraft and you do a bunch of little slices. Watch out. And I kind of take these and I ask myself, what is the area at each point? 1, 2, 3, 4, 5, 6, 7. And then I go and I plot it. And I want to see something. When I hit my wing, I'm going to have a big spike in area. When my wing goes away, I'm going to have a big drop. So get back to my tail again, they're going to increase again. And we're going to go down to 0. And so this guy, we're going to get right? Something like that. And now it's to match that for actually a bunch of different angles too. But if you want to match wave drag, I do not want it to look like this. This is bad. This means huge increase right here, big bow shock on my wing. Another big increase here, another big bow shock on my elevator. Things are not being smooth. So actually in the past, 2 years ago, MachWorks started with a small group of seniors and juniors. And there was a guy who wrote a master's paper to try and build the initial outer mold line geometry from the team that started last year. And it looked like this, called Blackbird. So what they did is they made an initial plane. It actually kind of looked like this guy. And then said, does it follow the area rule? It did not, wasn't even close. And then they went back to OpenVSP, our favorite little tool, and they started slowly altering the geometry, and they were trying to get it to match this curve. And they kept going and going and going, and they actually got pretty good. I mean, you can look at this, and then look at the hack saw body, right? And they look pretty close. And it explains this little divot in the body. It kind of shrinks down, because it's trying to compensate for the increasing area of the wing. I will note that there are big, big, big compromises to a geometry like this. Because, again, I'm not an aerospace engineer. I don't have a degree. But I look at that, and it does not look stable to me. It looks like a missile, because it is pretty much a missile. So it's pretty much acting like a rocket, but I don't see how we're going to get any good low-speed performance or anything, because our center of mass is here, and our things are here. I don't know. So you have to be pretty careful about it. I also didn't get a picture in here, because I just remembered it now, but there was a pretty famous aircraft that it looked the exact same. They could only get up to Mach 0.95, and then they went back and they followed this area rule. They just barely changed the geometry in a couple places to try and better fit that, and then it can go past the Mach 1. So it works. Oh, and I didn't mention the CD increase. So another big problem for us trying to go up to Mach 1 is that the coefficient of drag increases rapidly as you approach that speed. What's the name for it? Do you remember? I thought there was a name for it, but
It was something barrier.
yeah, drag barrier or something. So it's just between I think Mach 0.85 and Mach 1, it's a threefold increase in drag, something on that order of magnitude. So it becomes much harder, and doing wave drag stuff like this helps you out.
They thought it was impossible to break the speed of sound at first because it looks like an asymptote as you hit Mach 1.
And actually, if you go past it, it decreases, but that's only the coefficient decreases. Your drag doesn't increase. All right. Finally, wing sweep is another big part of transonic aerodynamics. So to try and explain that real quick, more drawing times. There's two schools of thought. One that's always published, and maybe you guys will convince me that this is more reasonable, and the one that I like to believe, which I think is better, but it's just me. So if I have a wing like this, we're kind of imagining that our airfoil is along this direction, which that's the school theory I'm not a huge fan of. And our velocity component is coming in here. And if I actually look at this, the component of the velocity that my airfoil section here should see should be this guy. And if this is Mach 0.7, then this is not triangles, but just go with me. You can imagine that's not reasonable, even remotely. But like, you get the point. This air is going to be less than the free stream. I can get closer to transonic because my airfoil is swept, and I can push a little bit further before I make a normal shock. However, I like to imagine if I had the same wing and it had a chord length like of C here, if I sweep it here, it's still C. But as I go down to here, it's no longer C. It's this extra long version. So kind of the ratio, like how the thickness to chord ratio on this airfoil is now a lot lower. So an airfoil that, that you have to get a big speed increase to go over the top. This, much lower speed increase. So as I decrease that thickness ratio, should decrease the speed increase. It's a lot of increases and decreases. But sweep keeps us from building normal shocks, it delays it. So if you ever wondered why like a commercial airliner, if you look this up, is like, conspiracy, they can go faster, but they don't. And it's like, why don't they just go a little bit faster to get me there on time? Well, that's because we just talked about, that really big coefficient of drag increase is happening as they start to approach transonic. If they go any faster than that, they have to burn a lot more fuel to maintain that speed. And so it's kind of like a commercial airliner's speed limit.
It's mostly the engine that can't handle the increase in speed passed around that.
I think the engine could, well, yeah, you'll start forming shocks.
Yeah, shocks forming
but I think they could probably find a way around it. But they just, like, why would they even bother? Like, there's no point. Why would they fight with that? So yeah, that, and that's another good point. Yeah, they can't go straight into the fan because you're going to start breaking things. Hopefully formation shocks doing change. Cool. All right, we made it through transonic. Any questions or thoughts or discussion for transonic stuff? Yes.
Why are the wings on that plane backwards?
Oh yeah, I haven't noticed that. I think NASA was just having fun. I think I looked it up as well last night. Like, there were some actual control benefits for them having that. I think this was another high angle of attack authority because the things in the front are canards, so they're mainly messing around with control problems. It's an X plane. The X planes do whatever they really feel like doing at the moment. Do you remember why? Oh.
Yeah, it helps with the phugoid mode, which is a very strange thing that happens to planes at relatively high speeds, where they trade altitude for airspeed and pitch at the same time, and they oscillate in a really weird way, and this damps that out faster.
There you go. But it also is just a wing sweep. So what happens if we go forward?
Just thought it was cool.
Yeah, it definitely looks cool. I can't lie. It looks awesome. Oh, there are some other benefits to wing sweep too, but a lot of them are mainly this. I think there's structural, and I think there's a case where you're trying to keep the root chord of your wing from stalling before your tip to keep roll authority and stuff like that. But
they also really severely decrease the amount of lift you get out of your wing by sweeping it backwards, so there's negatives to it too.
That's, yeah. Which is why the commercials are not that swept. Okay, supersonic. So we're going past 1.25. When I was at 1.25, the reason all the air can still be subsonic is because as I'm forming those shocks over the front of my airfoil right here, remember they're taking out energy and they're trading it for pressure and temperature and density. So I can go in at 1.25 and be forming a normal shock on the front, and then my flow over here or down here can still be subsonic. But once we get past here, you're supersonic the whole way through. So you can see there's bow shocks in the front, and then as they come off the back of the wings, they're still making these expansion shocks as they go back into the flow. So supersonic whole way through. Same challenges in Mach tuck and wave drag. As you're going faster, but I'm going to be having more drag from my shocks if I didn't design it for the hacksaw's body, hackstier's body. Although, in kind of some ways, this is simpler because you don't have any normal shocks that start messing with you. where you have to need to deal with both supersonic and subsonic airflow, although usually these aircraft also have to operate in both regimes anyways. But like, I always find it funny, like you kind of read like the X1 or whatever, they're dealing with trying to break the speed of sound, and they're like, the aircraft is shaking and shaking and shaking as they're getting through the transonic region, and then right when they like go past Mach 1 and like go into fully supersonic, it just like smooths out and the aircraft stops shaking. Because it doesn't have to deal with both of these types of airflow at the same time, and things seem to behave better. But don't worry, there are new problems from going faster.
The video from the Apollo movie.
I don't know that video. We can look it up though if we have time.
The X-15 and that exact thing happened.
Yeah. No, that's actually an amazing example. I should have had that. Missed opportunity. All right, so we're talking about temperature, intakes, and propulsion. So those are going to be our next big things. So intakes. Man, I love the Concorde. It is so cool. These are intakes from the Concorde. We were talking about these shocks, right? I erased it, but we have an angle. We have a new shock that goes right here. These intakes are messing with that phenomenon a little bit. So these guys are kind of isolating it, but there is a couple of different ramps in here that are changing where the shock location is going. So there's one coming off here, another one here. I'm not sure if that one's meant to also make a shock. But typically when we design these, you're trying to go for like two different conditions. So a really typical case is a 2 that's not angled. There's 2 angles like this. So this guy makes a shock, and this guy will make an also shock because it's flowing going this way, and now it's changed here to here, so I can do that like angle thing again and figure that out, and I'll have another shock. As I'm going through these, free stream pressure, free stream Mach, go through the first one, I slow down a little bit, I change direction a little bit, but my pressure increases. To go throughout this one, angle changes a little bit more, pressure increases again, I slow down a little bit more. And you can slowly find your way through what should the angle of this be, what should the angle of this be, so that when I go through this shock, I'm either like close to being subsonic, that is I go through like one more shock within the engine right here, that it becomes like normal. Or you can get by other things if we go for a scramjet. It's pretty common too that you have like a lip right here. If you have a changing geometry where I can change these angles a little bit, or I can change where this lip is, that they try and intersect right in the bottom right there, or that they go a little bit past it because you'll just get like a little bit of spill out this direction, but you still get like your big pressure increase. So Concorde is messing with this right now, and that's why these intakes look like this. So if you see these big triangular intakes where they have a leading edge and they go straight back and there's a lip a little bit backwards, that's what they're doing. They're using shock waves to give themselves a pressure increase. And what they're also doing is they're isolating the shock waves from the engine. So by doing this, I slowed my air down. So this air in here should be less than Mach 1. Because I'm going to have a ton of very delicate jet engine blades right here. And as Jordan talked about last time, shock waves plus engines equals breaking things equals explosion equals bad. So we don't do that. And then the last big thing is that when you have this going on, they get complicated. Because this intake has to operate both supersonic and subsonic. When I'm constricting the area like this, it means less thrust at lower speeds. So they end up having a bunch of like spillage flaps, and they're trying to control where all the air is going. Things get crazy. Okay. So inlet temperature. So we've kind of neglected the equations here, but there's one in the top, so don't worry. But this is saying T is temperature of the flow. TT is static temperature. Which means if I take a volume of air and I do all the work to slow this thing all the way down to no more velocity, it is going to trade all that speed, and it's got to put it somewhere. So it's going to go into pressure, and it's going to go into heat temperature. So I'm going to heat this thing up. So it can solve for TT pretty easily, actually. So if I do that for Mach 5 air at the 70,000 feet, I get a static temperature of 1,317 Kelvin, which is hot. Why is that a problem? I'm not slowing my air down all the way, right? I don't want to do that. My engine is taking in air. Air should be flowing over the airfoils. Should be. Well, boundary layer is going to be the new issue here. So, no matter how hard you try, you are going to have a boundary layer. And when we're going this fast, like Reynolds number, it just like is immediately turbulent. So, we have this small, very thin region of air around our airfoil. And in here, we're calling this turbulent, which in reality means like the air is not moving relative to the flow. It's pretty much stopped. So where did all that energy right here go? I'm moving along at Mach 5. Skin friction is slowing me down. When I come over here, I'm going into my boundary layer. I'm trading all of my speed. So that means that this area right here is going to be extremely hot. Same case in the engine too. If I have to slow that down to subsonic to burn it, I'm doing the same amount of work as it goes through shock waves. And as it goes through the shock waves, your temperature is going to increase. And materials can only take so much. Aluminum is going to melt at 933. So you have to be super careful about this stuff. And worse is that your engines will start to melt as well, because you are also going to put them through combustion. So you're going to burn it to make it even hotter. So how much can you take? Not a lot. The SR-71 is topping out at Mach 3.3. At least from what I read, like it could go faster. It would just start to melt. So it can't go any faster. And this becomes our problem like here on out. Because we can build new engines, we can put more fuel, we can put rockets on it, we can come in from orbit, but we cannot solve this temperature problem without a lot of engineering to mitigate it. We cannot remove it. So the first thing we can do is we do a new engine. So we were talking about this earlier, a ramjet. Jet engines have a compressor, right? We have to get our air, it's going to be slowed down, but I need to build up pressure so I can burn it, spit it out the back. If I already have all these shock waves, we're doing all this work, let's just use the shock waves. So that's all the ramjets are doing, is I'm using these normal shocks. So you can see this guy here. Shock up to there. There's actually another shock right here. And then remember, converging ducts, when you've got like hypersonic air, they don't speed up, they slow down. So this is going to actually slow down until it goes under Mach 1, and I have a normal shock in like right there. Because you can see how this changes from being a converging duct to being an expanding duct. So what should happen is I should get a normal shock right at the throat of this, and as I go past this, the flow will continue to slow down until it goes into this combustion chamber. I don't know if that made sense at all. So with that principle, I can make a ramjet instead. No blades, I can go faster. Nothing to burn up except the skin of the aircraft, which will be the next problem. But that lets us go a little bit faster. Let's see how much time we're in. So then we have our dual mode ramjets. So we can't have this presentation and not talk about the SR-71 that much, which I already have. Hold on. I thought I got our volume to work out. I didn't. That's okay. So we can watch this playing through. So you have your normal shock going in there. We're being fed into the main engine, this is our big compressor stage. Burning it. And the big thing is the SR-71 has this big afterburner in the back right here. And the idea is we're building all this extra pressure, and we're taking in all this air. And the engine can actually only take so much. And we want to take it out and put it into our afterburner instead, and it starts to act like this dual mode ramjet jet engine. Show the animation of the next part, please. I know, I love the J58 too. So we're going to put these little bypass ducts right between the compressor stage, and we're going to take it right back out and feed it right in the afterburner. And the really cool thing about this is that it could actually operate at higher efficiencies at its cruise speed of Mach 3 than it could at subsonic speeds, which is kind of crazy. That they made an aircraft that was better at flying fast. All right. And then finally, we have a scramjet. It operates almost the exact same as a ramjet, except we don't create a normal shock. Don't slow it down below the subsonic. And that's because we still have that same temperature issue in a ramjet. I'm still going to have that static temperature thing where I'm going to have to slow down to subsonic. I'm going to get all that temperature gain. I'm going to incinerate any known material known to man once I start getting past like Mach 7, which is going to be why this graph right here ends around there because there's just no material that can take it. And then scramjets are just the next step, next kind of logical iteration. Because I'm still having all these shock waves, I'm still going to use them to compress our air, I'm still going to burn it, but never subsonic. You'd have more issues in like lighting it because I can't have large regions of circulating air. So actually a lot of the ramjets that I've seen, they don't look like these nice images where they're like a clean like flow path where I can like go right through here. They're almost always like, I guess the ones I showed earlier also did that. But the ones I usually see flown are an intake, and then they like stop completely and go into some pipes, and they go into like a totally separate combustion chamber where the air is just like not moving very fast. But this, it's right through. We get to go faster speeds, but we still have some issues with temperature. And if you wanted to do dual operation, which man, if someone let me build this, I would be the happiest man in the world, would be to make a dual mode scramjet instead. And you can make a tri-mode too, Ram Scram turbojet. So instead you have your main intake, and then you have some sort of like bypass door that like feeds it down into your jet engine down here. Or the bypass door can change and it can get fed up into like a full-on scramjet into the back. But you'd have to get very creative with how you did this and made sure your shocks got handled properly. Because in here you need full hypersonic flow. In here you definitely do not want that. So we have problems. All right. And this is the same graph we showed last time. Turbojets, very efficient. Ramjets not quite as good, but like way better than rockets. Scramjets, no cap. Theoretically, I'd imagine there's a cap mainly on like material temperatures as we start exceeding 25. But theoretically, no cap. Because I could take Mach 20 air, slow it down to Mach 17, and I'm still going to get a big pressure increase. So it still works. Alrighty, now, Nathan's favorite here. We have all these new technologies. Go faster. We can enable much faster speeds. These guys are cheating. They're using rockets, but it's still cool. There's like very, very few technologies that have actually enabled hypersonic flight without the use of rockets, which we'll talk about in a second. You're still having our skin issues, so we're building that big boundary layer. Same problem. So the X-15 wanted to go really, really, really fast. They painted it pink, just for fun, like Barbie. But no, it was just a special type of coating, like ablative, that would totally burn off throughout flight, but give it some extra time. So you can imagine like this X-15 is like already kind of at the limit of what just like materials that we can make are at. You can try to do active stuff too. Like you can transpirate fuel through pores in the skin and try and bleed off things. Or we didn't talk about the X-15, which in the hottest parts of it, it would pass its fuel like around the skin and try and cool itself off and then pass it right back into the engine. So like they do a bunch of stuff like that. And the funny part too is the fuel would be kept in the wings or like within the fuselage, and it was already heated up to like something like really stupid, like 400 or 500 Kelvin already. So it's like extremely hot, but relative to the boundary, it's not that bad. But the flash point was like 2,000 Kelvin, so they had like little injectors that they had to put in, like I don't know what the firm is called, with the green flash for rocket engines. I don't know. It was SR-71's crazy. That's all we know. All right. I would argue that lift is like almost a non-issue at this point, because if you have just any sort of angle of attack on this thing, your lift just skyrockets. Because like I mess around doing random CFD, and it's like, oh, my lift on this tiny little meter-long plate is like 2 million newtons. I'm like, okay. So at this point, your thing is like, can I actually control this reasonably? Can I get this going that fast? Can I bring it back safely? So X-15 is landing at super high speeds in the desert because that's what it needs.
Can I add a fun fact about the X-15
Definitely.
control system?
Yeah.
It had to be so accurate that they spent like a lot of time modeling the delay it took electrical signals to go through wires inside this plane.
All right. And actually with that, you can probably add more to this, but we'll see. I found one of the funny things about the X-15 is its rudder. because it goes against like everything that we think about when we go to aerodynamics. It's actually still hard to see in this, but like that rudder is thick. Like, it is massive compared to its other surfaces and what we normally see in planes. And that's like a quarter of the fuselage in the back right there. But you could probably add to this. But from what like reading on this, like the moments that you can create are actually going down as you go faster. Like normally as I speed up, my plane will start to like correct faster. But this guy did not do that. And you can almost, if you really want a conceptual way, the way I was thinking about it is as I increase, I'm going to already have a shock wave because I'm having that big triangle. So it's going to be able to push me back into plane earlier than if I just had like a flat plate. It's almost like a pendulum dragging it back, but it's not actually how that would be working. And then also, the big note for this stuff that we're starting to get into is that the nose is not sharp. You can see the front of the aircraft is like a big ball. And if you actually looked at the rudder, it almost looks like it's coming to a point. But it comes to a rounded, blunted leading edge. And the wings are kind of close. They try and match this. This is a typical supersonic airfoil. But you don't want these nice sharp edges because the way the shocks form, it ends up making things a lot hotter. So it's very typical, especially for like re-entry, that you have blunted bodies. Blunted bodies are better for heating than the sharp ones, but not as good for go fast. Anything you want to add to controls?
Yeah, I mean, it is funny. The rudder that they used in this one steered using flow separation off of it. So you steered it the wrong way to what you would think to get the aircraft to turn.
Nathan, I got a controls question. So I heard in the 50s and the 60s, like with the MiG-15s and the F-86s, that they had like supersonic lockup. How did we like overcome that?
A lot of it was like just digital age and things becoming more intelligent. But yeah, that happened because, like literally, like I said, signals couldn't move fast enough through analog systems that depended on like basically like dampers from like systems classes. Those were like mechanical components they used in control systems, and they couldn't handle actuating that fast, basically.
Okay.
Alrighty, X-43 might be one of my favorite aircraft. It's still cheating, but it didn't cheat quite as hard. So it got boosted up to like Mach 5 by a big giant rocket, which we'll see in a second. And then it ignited an actual scramjet and then flew up to around Mach 10. So this is currently the air-breathing powered flight speed record is 9.6 set by this thing. And as you'll see, it's actually like only like a meter long. It's not that big. As we were just talking about, controls are still a problem. There's no point in having these giant elevators. When you're flying at Mach 5, any sort of tiny control deflection is going to give you a really large response. So no point. It's also hilarious to me that this entire aircraft, it's actually just a scramjet. It's only a scramjet. So the leading shock coming off of the nose up there is going into the engine. And then as it burns here, this is the expansion area for the plume to get it to expand and give it more thrust. So it's just a scramjet with wings on it. It's not carrying any payload, but it's cool. And the same issues as we talked about before. There's quite a bit of other literature that the center of pressure is moving around, so the elevators in the back have to compensate. It is super cool. So I have we'll just watch it. We'll see if we can watch. I don't have the video for it, but I thought I was gonna have sound. Let me see. That's it right on the front of the thing. So you can see how big that nose is compared to people. This was April 2004, I think. Yeah. It's pretty small on a giant engine. You can see the flap right there move as a full-flying elevator. Rocket, rocket, rocket. Yeah. Pretty cool stuff. This is like tracking from a jet. Sadly, they did not want to give maybe they did, but I don't think they really had live video, because I do not know what this is. They have this guy, though. Yeah, so that is the X15. Yeah, hey, I was right, April 2004. All right. Alrighty, so the next question is, what's past that? So this is kind of a graph that gives you kind of some perspective on like the full regime of how fast we can go. So x-axis we have Mach going through here. Well, Mach 40 is pretty ambitious. And then we have our height. So the big thing to notice here is that they have this thing called the heat barrier. So I'm going Mach 30, and I'm only 50 kilometers up. I'm like well within the normal atmosphere. It's like an asteroid. They're just going to incinerate anything that is moving that fast. So if I want to go faster, I have to stay higher up where the density is lower. And I have to slowly bleed off my speed. Because when it comes to this stuff, everything is just rockets. As you can see right here, the X-43 was the peak of air-breathing propulsion. And it was, up here you can see how high and where we're at. Like that is, in this section right there of possible like planes and SSTOs that could go like this direction, X-43 is as far as we've gotten. Everything else is things that are coming back in from orbit, or as I'll note in a second, are coming in from suborbital, and they're trying to re-enter and control themselves. So when we're talking about past Mach 10, everything is mainly just re-entry. And I have a couple of fun examples. Unsurprisingly, a lot of things are just military use at this point. But I was going to note the glide vehicles because they are part of the world now of aerospace. And I could not find a lot of great documentation on these, unsurprisingly. But I'll just draw on a chalkboard because I don't know how much harm I could do. But the entire idea of a glide reentry vehicle is, it's like normal ballistic weapons where they're trying to be in a suborbital path and they're trying to hit something, but instead they hit short. So normal, and then these guys, they boost like here, and they're trying to stay out of the horizon line, and they re-enter, well within here, about like as low as they can go, and they maintain their kinetic energy all the way down. So there's way more controls problems, thermal problems to try and make that work. But in terms of current hypersonic work past Mach 10, that's pretty much all I know. There's also other stuff like reentry vehicles, like the X-37, our autonomous shuttle that also has no documentation on it too. It's also trying to do similar problems of how do I reenter with control. And then I also threw in here Skylon, which is an SSTO. Has anyone ever heard of Skylon or seen that? Yeah? That's great. We love it. They sadly are not doing Skylon anymore, which is extremely sad. But their engine, the Sabre engine, was trying to take in air and then cool it down through a chiller. They had this like special technology that they kept secret, that they'd slow down the super high temperature air that we were talking about and like dissipate the energy in another way, and then pass it into an engine, and then they combined it as a dual mode, essentially ramjet jet engine, and then added a rocket component to the side of it. But it was pretty cool. It did not get very far. One day, I really hope that we can find a way to build SSTOs with all this technology, and not glide reentry vehicles, but it's just me. Alrighty. A couple more plans that I couldn't get put in here. So there's always trade-offs. Usually with us, we want to go faster, we're going to get more heating. If we're trying to decrease our drag, more heating, harder to control. Trying to understand the flow field around these vehicles is like kind of the hardest part. I didn't really talk about it that much, but there do exist wind tunnels for hypersonics. But when you build a tunnel and you have it expand, so I have really high pressure in here, high pressure, and I get hypersonic flow in here, it's going to expand. But as it expands, you actually lose temperature. So my temperature goes down, and my pressure goes down, but my speed goes up. And you get issues. So if I take like normal oxygen or even just like nitrogen, and I put it into here and I expand it, and I put it into a straight wind tunnel, I get problems because the temperature is so low that the nitrogen starts to liquefy. So the only way to combat that is by heating this guy up with a heater, but then your pressure's already low. So you can see like you can't really emulate like hypersonic flow conditions in wind tunnels unless they're like extremely expensive. And even if they can, they're only giving you like a tiny aspect of it. So like one common type is you're putting in a very specific gas and heat, and you're trying to emulate like only the heating. And the one I was talking about where they cool down, like maybe they're just trying to figure out what are the shock directions and interactions. So you can only get pieces. So that's why like CFD is a new big part, which I advertise because that's what I do. Cool. Venture Star was another stupid SSTO concept, but it has aerospikes and looks cool, so I love it. MiG-25 Foxbat is the fastest fighter jet, at least that I know of. And the XB-1 Valkyrie was a US bomber that flied like crazy fast. But its fun fact is it has these little like wingtips on the bottom, on the edges. So what it would do is it would purposely make shockwaves that like reflect on each other underneath the fuselage and create pressure under itself to essentially like lift it up and make it more efficient at cruise. So some crazy planes. Anything else you wanted to add, Nathan?
Oh yeah, this one used engines from just a missile. They just put.
Is that the one that could only fly like once or twice?
It could fly like 12 or 13 times before they had to replace the engine because it was not. It was designed to be a single-use engine because like the missile doesn't really land most of the time, at least not in one piece.